Study Unit 6, Lecture 4. Lectures 4 and 5 once again has a look at converters and rectifiers, but instead of considering single-phase circuits, three-phase or rather n-phase circuits are considered with a focus on three-phase circuits. Switching topologies aside, when three-phase converters are considered against, or rather compared against single-phase converters, three-phase converters will have a higher DC output voltage, a higher DC output power, and a higher output ripple frequency. The reason for the first two is quite simple. There are now essentially three supplies driving a single output, and the reason the output ripple frequency is higher is because there is essentially a frequency multiplication which is happening by having three supplies each out of phase driving a single output. Just to recap on some notation and phase conventions used in describing three-phase sources, we'll just quickly go through how to define the different phases in terms of a supply sinusoid. So the first reference phase can be any phase, but for say for example phase A relative to neutral can be written as a shorthand VA with an arrow on top. And this first phase will have an angle of 0 degrees because it is the reference phase. And it will have the form which is pretty commonly seen in the single phase application, which is simply V sine omega t. Subsequent phases will have a different phase offset but will have the same amplitude and frequency. So in a three-phase system there are three phases, so the total phase shift for each phase must add up to 360 degrees. So the reference phase will be 0 degrees, then there will be phase B which will have a minus 120 degree offset, and phase C which will have a plus 120 degree offset. So these signals have the same frequency and magnitude as the reference phase, but with a phase shift relative to 0. So it's pretty easy to visualize graphically. You have the reference phase A over here, and then B will be 120 degrees offset in phase, and C will be plus 120 degrees. And the remainder angle between B and C will also be 120 degrees. And together this will add up to the full 360 degrees. The individual phases are described relative to the neutral terminal, but a voltage between different phases can also be described using the following notation. So the voltage difference between phase A and B can be written as phase A minus phase B, and then writing down the expression for each. So phase A minus phase B is root 2 V sine omega t minus root 2 V sine omega t minus 120, and these can be solved using double angle formula to give root 3 root 2 V sine omega t plus 30 degrees, or plus pi over 6 if you're working in radians. So this description of each phase relative to a neutral terminal is useful when using a star transformer where there is actually a neutral terminal. But when a delta transformer is used, there is no neutral terminal, and the phase voltages need to be described in terms of each other. So then this VAB notation is useful. So here is an example of a three-phase half-controlled bridge converter. The reason why it's half-controlled is because half of the switching devices are diodes, so there's no control over when they switch, and the other half are thyristors. In this topology there is no neutral terminal, so each supply voltage or each phase needs to be described in terms of the other phases. So the three inputs to the converter are described by the following three equations. It's a VAB, a VBC, and a VCA. Each is of the form Vmax sine omega t plus or minus some other phase shift. So for VAB the phase shift is plus pi over 6, for VBC it is minus pi over 2, and for VCA it is plus pi over 2. Before the output voltage of the circuit is analyzed, it should be noted that there are plenty of diodes in the circuit. Excluding the freewheeling diode, diodes D4, D6, and D2 will prevent the output voltage from going negative, so a voltage inversion at the output is not possible. The purpose of the freewheeling diode D1 is to help with power transference to the load, and this is the same as for a single phase converter where a freewheeling diode is used to assist the converter. The mean output voltage is given by the summed contribution of each phase in each phase's bridge to the converter. So operation is exactly as that of a single phase converter, except there are now three phases each out of phase which contribute to the output. This mean output voltage is given by root 2V multiplied by 3 times root 3 over 2 pi multiplied by 1 plus cos alpha, which simplifies to 2.34 times input voltage times 1 plus cos alpha, where alpha is larger than 0 but smaller than 2 pi over 3. So the value of the delay angle alpha will determine what the maximum output voltage can be. So there are two distinct cases for alpha. There is a case when alpha is small, and there is a case when alpha is large. It's still smaller than the maximum allowable delay angle. So the key distinction for alpha less than pi over 3 and alpha larger than pi over 3 is how many controlled and uncontrolled phases there are during each conversion cycle. So for alpha less than pi over 3, there are 6 pulses during the conversion cycle. For a much larger delay angle alpha equal to, or rather larger than pi over 3, there are only 3 pulses per conversion cycle. What this simply means is that when the angle is small, there are more conversions per total cycle than there are when the angle is large. Because there are more conversions, the output voltage will actually never drop to 0, and thus this mode will always operate in a continuous current mode. For the case of a large alpha, continuous load current is also possible in the presence of a freewheeling diode. The three-phase half-controlled circuit can be modified to a fully controlled circuit by adapting the topology to the circuit shown here. In this circuit there is a neutral terminal for the current to flow back to. There are also now only 3 thyristors, one for each input phase. Once again, the output is determined by the delay angle alpha. For this circuit, the delay angle alpha is the angle which is the earliest point at which one of these thyristors will start to conduct. So shown in this graphic over here, there will be some period where T1 conducts, then T1 will turn off and T2 will conduct, and then again T2 will turn off and T3 will turn on, and then conduction will be from the third phase, phase C. So how the control works is that there is no external control which determines when the thyristors are on. So whether the thyristor is on or not is determined by the delay angle alpha, and whichever thyristor has the highest instantaneous anode potential will turn on, and in turning on will reverse bias the other 2 thyristors, causing the thyristor which is on to conduct and the other 2 to be off, so they will not conduct. So once again shown here on the graph, there will be some period where T1 conducts. Once the delay angle causes T2 to be more positively biased, then T2 will conduct and T1 will turn off. Eventually the same will be true for T3, and T2 will turn off and T3 will conduct, and so on. So a general expression for the output voltage for an n-phase converter is given by root 2v divided by 2 over pi over n, where n is number of phases, multiplied by the integral from alpha minus pi over n to alpha plus pi over n of cos omega t d omega t. This can be simplified to the square root of 2 multiplied by the maximum input voltage multiplied by the sinc of pi over n multiplied by cos alpha. For a 3-phase system, n just simply becomes 3, and the output voltage is given by 1.172 v cos alpha for alpha between 0 and pi over 6. This expression here, where alpha is between 0 and pi over 6, is for continuous or discontinuous load current. For discontinuous conduction, the delay angle alpha is between pi over 6 and 5 pi over 6, and this has a slightly different expression of 3 over 2 pi multiplied by root 2v multiplied by 1 plus cos of alpha plus pi over 6. So for continuous conduction, the output voltage will always be larger than 0. So depending on the alpha during discontinuous conduction, the output may be positive, it may tend to 0, but if alpha is larger than pi over 2, then the output will be driven to below 0 and the converter output voltage will be inverted. For cases where alpha is larger than pi over 2 and inversion will occur, it is assumed that there is some EMF load or back EMF in the load which will assist the reverse current flow which is going to take place. So back to the graphic. Here are 3 examples which represent the sort of 3 different areas where alpha can fall. The first, alpha is less than pi over 6, so here there is an output voltage which on average is larger than 0. In this example over here, alpha is approaching pi over 2 and is larger than pi over 6, so here the average output voltage will be closer to 0 and there may be discontinuous conduction. Finally, in this example over here, the angle alpha is very large, in fact it is larger than pi over 2, and the majority of the cycle for each conversion part, or each step of the conversion, is actually in the negative part of the input cycle, and this will cause the output voltage to go into inversion and be negative. If a negative voltage is not desired, or rather this voltage inversion is not desired, then it is possible to insert a freewheeling diode in shunt with the load. This freewheeling diode will essentially prevent the output from dropping to a negative voltage. When a freewheel diode is included, then the output voltage remains unchanged for alpha less than pi over 6 and will be 1.17 V cos alpha. If the freewheeling diode is present, then these negative contributions of the input supply voltages will not contribute to the output voltage because the voltage will decrease and then simply hit the diode limit at 0. So in short, the diode prevents any type of voltage average contribution from parts of the cycle which fall below 0. This also concludes this lecture. The next lecture will continue with three-phase converters and rectifiers.